Hello everyone. Today we're going to understand calculus. We're not going to master it, we're not going to learn all of the rules, we're just going to get an intuitive feeling of what it is. One of the things that calculus can help us with is calculating areas and volumes. So if we take the standard shapes that we know already, if we've got a rectangle, we can say length times width is equal to the area. Area equals length times width. In the same way, if we've got a circle with a radius of r, then the area of this is pi r squared. If we have a triangle, we know that the area of a triangle is if that's the base and this is the height, then the area is half of the base times the height. So we are using formulas here. This is the idea. Now imagine a random shape. Say we've got this. It will be very difficult to calculate the area of this shape. But imagine if we rotate this shape and end up with something like this. And we see that it's not two-dimensional but three-dimensional, and it can be filled perhaps with the fluid. Now this is something that calculus can help us with, because we haven't got a formula for this, but calculus can do it for us. So here we go. So let's imagine we have a graph. And a function, we'll say this function. And this function is not a very well drawn graph. I was never a great artist. This function is f of x equals x squared. Now let's mark on here some points along this axis. 1, 2, 3, 4, 5, 6. And so we want to know the area between the point 3 and the point 6. We want to know the area under here. How would we do that? Well, you may have seen this long S-shaped thing. This just means the sum of. We call it the integral. So if we have this function here, x squared, we say the integral, or the sum of, x squared. We have a dx here, it just means with respect to this function. We can say that we add 1 to the exponent here for this function, and then we divide it by whatever this new function's number is. This is not perfect mathematics, but we're just learning, we're intuiting what calculus is doing for us. So from here, if we want the area under this curve from 3 to 6, then we say from 3 to 6 we have this function. So we would say we substitute 6 for this x, and then we subtract it, or rather we put this 3 in. Here, I'll show you, it's easier. So we put 6 cubed divided by 3 minus, and we substitute this one in, 3 cubed over 3 equals area under that curve. That's the area of that curve. So these are the powerful things that calculus can help us with. Let's imagine the next thing. We're going to look at slopes or gradients. The gradient of a curve. The gradient of a line or the gradient of a curve. Calculus can tell us the gradients of curves. So let's have a curve, any old curve. And if I want to find the gradient of this somewhere, then I would choose, say, this point here and this point here, and I would say, what's the gradient through there? And we know that a gradient is equal to rise over the run. Rise, run. So go over here, gradient is equal to rise over run. But this graph is changing all the time. Its gradient is changing everywhere along it. So from here to here, the gradient is approximately like this. That's terrible drawing. But here to here, the gradient is like this. So it's a continuously changing line. So what do we do about this? Because if I want the gradient at a precise point, exactly here, then I'm only ever going to get approximations, because I'm taking another point, say here, and then doing the rise over the run for that. But I'm never getting the exact point, this exact point's gradient. So what we do for this is differentiation. So let's imagine this curve's function, this curve's rule is expressed by, let's say, 3x squared plus 4x plus 2. Then we would say f prime of x, or perhaps dy by dx. This means the same thing as this. If we say the rule for finding the slope, the gradient of this function, is given by this, 6x. What we've done is we've multiplied this 2 by this 3, and then we've reduced this exponent by 1. So this is 6x to the 1, but we'll miss it out because it's not necessary. Then we say plus 4, and then we multiply what would be a 1 here, bring it to the forward, so that's our 4. But because we've reduced this by 1, this becomes x to the 0, and it's left as it is. And because there's no x here, we leave it. So this describes the gradient of this function. Wherever you are on that line, this is the value you get for that function. So we see understanding all of this is just about understanding the rules, applying the rules that we have. We can learn them later, but just getting the fundamental grasp, the concept that what you're doing here is solving many, many problems in calculus that are to do with changing rates of change. Now let's imagine we have another graph, and this graph represents population growth, we can say like this. And we can say over time, this is time, and this is population. Oops. We can see how population grows over time, and we can use, again, we will use calculus to see what the instantaneous rate of population growth is given a particular time. And at a particular time, a particular point in time. And this gives us a very powerful tool so we can understand what exactly is happening and how we can affect and change things, how we can solve mathematical and engineering problems. So the fundamental thing I want you to take away from this today is that you can do it. It's just lots of simple things done in a row. You learn the formulas and the rules for what you're doing. You can already understand that you're looking for volumes of things or areas under things. They're quite simple when you can intuit what you need to do. We look for gradients and slopes. That's quite easy too. You know, rise over run, and it's just an extension of that. So the area and volume, the area and volume problems are generally given by the sum of things, and the gradient, the slope, is given by the derivative, which can also be written like this. And that's it for today. If you enjoyed this video, please subscribe, and there'll be more coming soon.